In this video lecture, we will introduce the concept of current in electronic circuits. The operation of electronic circuits is based on the controlled motion of charge. We will talk later on about how charge can be set in motion. Charge moving gives birth to a current. By definition, the electric current is the total charge that passes through some cross-sectional area A per unit time. Theoretically, this cross-sectional area could be a disk in any material like a gas, plasma, or a liquid, but in the case of an electronic circuit, typically this cross-sectional area is a slice through some solid material, some metal, for example, or a semiconductor. Let us consider a metal wire, for example, a copper wire. The charge in the wire is represented through elementary charge carriers. Let us suppose now that we are able to apply some force to each individual charge carrier and to move them, for example, to the right. So, if delta Q is the amount of charge passing through a section A of the wire in a time interval delta t, then the average current I sub A, where A stands for average, is defined as delta Q divided by delta T. Note that if N is the concentration of the charge carriers in the wire and the charge carriers move at speed V, then the amount of charge delta Q in the shaded volume is given by the concentration N times the speed V of the charge carriers times delta T times the area of the cross-section of the wire. If we take the limit as delta T goes to 0, we can define the instantaneous current I as a function of T as the instantaneous rate at which the charge passes through the section of the wire. The rate of change of the charge with time represents the definition of the electric current. Given the definition of the current as the time derivative of the charge, the unit of measurement of the current will be given by coulombs per second. This unit of measurement is also called the ampere. So 1 ampere is equal to 1 coulomb per second. Sometimes the word ampere is abbreviated to amp. For typical electronic circuits, 1 ampere is a pretty large value. This is the reason why when we talk about currents in electronic circuits, we use metric prefixes in front of the unit of measurement. So we typically talk about milliamps, microamps, nanoamps, or picoamps, or even femtoamps. A current can be measured using an instrument called the amperometer. Note that when considering the units used to measure some physical quantity x, the symbol x between square brackets means the measurement unit of x. As we saw when we defined it, the electric current is not a fluid but consists of elementary unit or quanta of charge. Of course, in the case of an electronic circuit, the elementary unit is the electron. The electron is just one of the elementary particles making up atoms. An atom consists of a nucleus, including positive charge carriers called protons and neutral particles called neutrons, and electrons around the nucleus bound to the nucleus with a force which depends on the atomic species we are considering. The atomic number of a given chemical element is the number of protons in the nucleus of an atom of that chemical element. If that atom is electrically neutral, then the number of electrons in that atom is the same as the atomic number. The atomic number is typically indicated with the letter Z. The atomic number of any element can be found in the periodic element table. For example, hydrogen has atomic number 1, carbon atomic number 6, aluminum has atomic number 13, silicon has atomic number 14, copper has atomic number 29, gold has atomic number 79, and uranium has atomic number 92. The behavior of electrons around the atomic nucleus is described by quantum mechanics by means of so-called wave functions whose modulus square represents the probability of finding an electron in some point in space. However, for the purpose of understanding the properties of electrons, it may be useful to use the so-called planetary model, according to which electrons move around the nucleus along well-defined orbits. For example, in the case of oxygen, you have 8 protons in the nucleus and 8 electrons moving around it. In quantum mechanics, actually, orbits take a different name. They are called orbitas, just to mark the difference with respect to planetary orbits as we know them. In general, electrons will be located on orbits at different distance from the nucleus, depending on the chemical element we are considering. Electrons tend to fill up the orbitals starting from those which are closer to the nucleus, or to be more precise, from those at a lower potential energy. Some of the chemical and electrical properties of materials are determined by the characteristics of the outermost orbitals or by the peripheral electrons, also called valence electrons. An atom where the number of electrons is different from the number of protons is called an ion. Changing the number of protons in the nucleus of an atom is typically a very hard task. Changing the number of electrons is much easier. So, an atom where the number of electrons is smaller than the number of protons in the nucleus is called a positive ion. So the symbol H plus represents a positive hydrogen ion. So a hydrogen atom where an electron has been removed from around the hydrogen nucleus. Actually, the only electron which we have in a hydrogen atom. As a further example, A plus represents a positive aluminum ion, where one electron has been removed from around the nucleus. A negative ion is an atom where the number of electrons is larger than the number of protons instead. For example, the symbol O minus minus indicates the doubly negative oxygen ion, so an oxygen atom with 2 electrons more than in the neutral configuration of the oxygen. Pluses and minuses in the above symbols represent the charge of the ion. Note that the ion charge does not change continuously, but can only take discrete values, integer multiple of the fundamental electrical charge Q, given by 1.6 times 10 to the minus 19 coulomb. This is actually the charge of the electron changed in sign, as the electron is assigned a negative charge. Protons and neutrons in the nucleus of an atom are bound together by nuclear forces. Electrons are bound to the nucleus by Coulomb forces related to the electric charge of the electrons and of the nucleus. The force binding an electron to the nucleus, in particular for the valence electrons, which are the electrons located on the outermost orbital in an atom, is not the same in every element. This property is quite important because the fact that a more or less large amount of current can flow through some material depends on the density of free electrons available in that material. A free electron is an electron which is no longer bound to a nucleus and can move freely when some force is applied. We can actually distinguish the materials used in electronic circuits according to the amount of free electrons they can provide, or, which is the same, the strength with which valence electrons are bound to the nucleus. Conductive materials, or conductors, can provide approximately one free electron per atom. A conductor can be modeled as a reticle of atoms in a cloud of strongly delocalized, which is the same as weakly bound, electrons. The concentration of free electrons in conductors is of the same order as the concentration of atoms, around 10 to the 23rd per cubic centimeter. Metals like aluminum, silver, copper, or gold are typical examples of conducting materials. In an insulating material, also called dielectric material or insulator, valence electrons have an extremely strong bond with the nucleus. So, when an external force is applied, no charge moves and no current can be observed. Typical insulating materials are different kinds of ceramics and silicon dioxide, which is largely used in the microelectronic industry. Semiconductors behave like insulators at low temperatures. Their behavior gets closer to that of a conductor if the temperature is increased. This can be qualitatively explained by the following consideration. The temperature increase is responsible for breaking the bond of valence electrons with the nucleus, therefore increasing the free charge concentration. Typical semiconductors are silicon, germanium, and some compound materials like aluminum arsenide, gallium arsenide, and indium phosphide. Semiconductor properties can be changed by adding impurities, which are atoms of different elements like boron, aluminum, phosphorus, and arsenic, in very small concentration, in the order of 1 part per billion. This process of adding impurities in semiconductors is called doping. The current flowing through a circuit component is by convention represented by means of an arrow indicating the direction of the current and a letter, which is the name assigned to the current and may also refer to its numerical value. For example, in one branch of a circuit, we may have a current I flowing from left to right. This current may have a value of 1 milliamps. However, the numerical value is not necessarily indicated in the scheme. Note that the arrow indicates the direction of the current as if it were made of positive charge carriers. We know by now that the moving charge carriers making up the current are actually electrons. So electrons will be actually moving in opposite direction to the conventional direction indicated by the arrow. This is not a problem at all. Negative electrons going one way are equivalent to positive charges going in the opposite direction. In fact, all the formulas used in electronics, such as Ohm's law, which we will be discussing later on, pretend that the current I is made up of positive charge carriers. We will always use this convention. Consider now this example. Suppose that we have a conductor carrying a 200 milliamp current. The current is flowing from left to right in the conductor. This means that we are conventionally assuming that positive charge is flowing from left to right in the conductor. Now the question is, how many electrons pass through a section of the conductor in 1 second? Of course, electrons will be flowing in the opposite direction to the one indicated by the red arrow. By definition, the current is given by the amount of charge passing through the section in a given amount of time delta t. If we know I and delta t, we can obtain the amount of charge, delta q. Here, delta q is of course the amount of conventionally positive charge. The amount of charge delta q sub e given by the electrons passing through the same section will be given by I sub e times delta t, where I sub e is the electron current flowing through the conductor in opposite direction to the conventional direction. Of course, IE is equal to minus I. So delta QE will be equal to minus I times delta T, which is minus 200 milliamps times 1 second, which amounts to minus 200 millicoulomb. Recall that the electron charge is minus 1.6 times 10 to the minus 19 coulomb. So eventually, the number of electrons passing through the section of the conductor in 1 second will be N sub E equal to delta Q sub E divided by the charge of the electrons. This is approximately equal to 1.25 times 10 to the 18th. One more word about positive and negative charge carriers. We saw that in conductors, only electrons are free to move, not positive charge carriers, which instead are fixed in the lattice network of the conductor. This situation may change if we consider other materials or media. For example, a positive ion flow is possible in some liquids, gases, and plasmas.